In this lesson, we are going to introduce the divide and conquer algorithm. In the course of the divide and conquer algorithm, we will introduce our roles in order: the concept of divide and conquer algorithm, how to use recursive methods and dynamic programming method to solve problems. In the end, we will discuss the application of the divide and conquer algorithm and the summary of key points. First of all, we need to know why we still need this divide and conquer algorithm, since there are so many algorithms already. There are some problems that will consume a lot of time by using brute force exhaustive algorithm only, and using the greedy algorithm will get incorrect answers. At this time, we can use the divide and conquer algorithm to solve our problems. So, what is the divide and conquer algorithm? We will start with the steps. The first step is to divide the original problem into smaller and independent subproblems of the same type as the original problem. The second step is to solve, or conquer. When the final subproblem is simple enough to be calculated, we will calculate the answer to the subproblem. The last step is to compose, that is, to compose the solutions of each subproblem to give a solution to the original problem. This is also a top-down algorithm problem-solving strategy. So, what are the key challenges of these three steps? The first one is to decompose, so we need to think about how to decompose the original problem by observing the regularity of the problem. There are two ways to solve problems. If the problem is small, it can be solved directly. Otherwise, we use the recursive methods that are described later to solve the problem. The final method of composing is also very important: how to compose and compute after solving the decomposed problem. The divide and conquer algorithm has three advantages. The first advantage is it can simplify the difficult problem into easy-to-implement parts. The second advantage is it can reduce the complexity of our time and space and improve the efficiency of the program. The third one is it can be converted into parallel processing to make it more suitable for cloud computing. So, when can the concept of divide and conquer be used? The quick sort and merge sort mentioned in the sorting algorithm use the original sequence of number to continuously decompose into two parts. When the sequence of numbers is decomposed to only 2 digits or 1, the order of the digits can be determined. The difference is that merge sort also has the process of merging the sequence of numbers for the two decomposed parts. The common ways of implementation include recursive calls and dynamic programming. Next, we will introduce the problem-solving thinking of these two methods. First of all, we will compare the efficiency of the divide and conquer algorithm in sorting problems. We can observe that we have already learned from the search and sort chapter. The insertion sort, selection sort, and bubble sort, these three sorting algorithms, compared to the two new sorting algorithms that use the divide and conquer algorithm, quick sort algorithm and merge sort algorithm. Which sorting algorithm seems to be more efficient in sorting problems? Which one seems to be not so fast? Of course, the time complexity will also be affected by the difference in the original data. Nevertheless, on average, using the divide and conquer quick sort algorithm and merge sort algorithm will be more efficient than the selection, insertion, and bubble sort algorithms. Next, we will discuss how to use recursive divide and conquer. There are three recursive steps. The first step is to find out the termination condition for the recursive call of the problem. That is, how small our problem must be decomposed so that it can be calculated directly. The second step is we need to find out how to decompose it into two or more recursive functions or a recursive relationship. The final step is what kind of information to return after the recursive call, or how to merge or compute in order to get our answer. After having a general idea of the steps, what are the key points that need to be paid attention to in the recursive call? There are 5 key points to pay attention to in recursive call. The first one is what parameters need to be passed when calling. The second one is what information do we want returned when returning. Next is whether there are any special circumstances that we need to consider additionally. Furthermore, is the recursive depth too deep that the complexity will waste too much time and space? The final point is to note whether the calls were made repeatedly. If they were, is dynamic programming needed to fix it? Next, we will learn how to apply the divide and conquer algorithm. Application of divide and conquer algorithm: paste L-shaped tiles. On a 2n times 2n plane, there is a 1 times 1 gap, which is the small gray square in the picture. And for the remaining 2n times 2n minus 1 space, we need to fill it with L-shaped tiles, which are these L-shaped tiles with different gaps in red, green, blue, and yellow. How do we fill them? Many students may think that we use the brute force exhaustive algorithm to solve this problem, but there will be this situation like the picture on the left, and the 2 grids with question marks on the upper left will not be able to be filled. Observing carefully, we can find that, in fact, as long as the problem is reduced to a 2 times 2 square, it is very easy to choose one of the 4 tiles and paste it. So, how do we start? Let us disassemble the 8 times 8 plane into 4 times 4 subplanes, because the 4 times 4 subplane in the upper left corner already has a gray gap. And the small problem after disassembling should be similar or the same, so it can be solved from small to large. So, we're going to make each of these other 3 planes, which are the 1, 2, and 3 subplanes, have a gap too. At this time, as long as the gap is filled with the red tile on the upper left at the juncture, the 4 times 4 subplanes will each be filled up, and the problem can continue to be recursive to the 2 times 2 sized subplanes. Next, we will disassemble the 4 subplanes separately. Take the one on the upper left corner as an example. Continue to disassemble it into 4 2 times 2 planes. Similarly, the one on the lower left corner has a gray gap, so fill in the blue tile to make sure the other 3 also have gaps. Now we almost have the answer. Is it easy to select a suitable tile to fill in the 2 times 2 plane at the bottom left corner now? Next, we just need to get the solutions for each of the smallest planes, and then we can combine them into the solution for the 4 times 4 plane. The tiles can be put together using similar methods for the other 3 4 times 4 planes, and then combine them into the solution of the 8 times 8 plane. This is how divide and conquer uses recursion. If this problem is to be solved by a program, what information needs to be entered? And how should the parameters and return values of the recursive subroutines be designed? Application of the divide and conquer algorithm. The problem of nearest distance between 2 points on a plane space. This application is to calculate the closest distance between 2 points on the plane. There are endpoint coordinates x1, y1 to xn, yn on the plane. Please find the 2 closest points among them. The formula for the distance between any 2 points is xa minus xb to the power of 2 plus ya minus yb to the power of 2. Then square root. This problem occurs in many applications, such as in air traffic control. We may want to monitor 2 planes that are too close because it means they might collide. When we use the brute force algorithm to solve the problem, that is, when we calculate the distance between all points 2 by 2, we will get the time complexity of n to the second power. So when n is maximum, we need a very long calculation time. If we use the divide and conquer algorithm recursive calls, we only need the time complexity of n times log n to the second power. Next, we will learn how to use the divide and conquer algorithm to deal with this problem. First, we will sort the input points according to the x-coordinate and find the middle point in the x direction. Next, we divide it into the left half and the right half according to the middle point. We then use recursion to find the minimum distance in the left and right parts and set them as dl and dr respectively. Finally, we set the minimum value of dl and dr to d. In the 5 steps above, we get the upper limit d of the minimum distance. Now we have found the minimum distance d, but there is one more condition to consider: how to deal with points that cross the left and right sides. The first step we are going to do is to find all the points with x-coordinates that are closer to the middle vertical line than D and record them in the array script. Then we sort the points in strip according to the y-coordinate. Next, we find the minimum distance from strip and set it to ds. Many students think this is a step with a time complexity of O of n to the second power, but this is actually wrong. The time complexity of this step is actually only n. This can be proved geometrically. For each point in the strip, we only need to check the following 7 points at most, as shown in the figure on the right. The last step is to return the minimum distance d calculated by the recursive call. and set it to the minimum value of dl dr ds. Let's analyze the time complexity of this problem. The first place where time complexity appears is after we divided all points into two groups. The recursive call finds the point that spans the area and with a distance of d, so the consumed time complexity is O of n. Next, we consume n log n time complexity in sorting by time. The last place that involves time complexity is when we are trying to find whether there is a point in the middle with a span distance less than d. The time complexity of this step will be n. We set t of n equals 2t of n over 2 plus O of n plus O of n log n plus O of n. We can simplify the previous formula to 2t of n over 2 plus O of n log n. Then we can simplify the previous formula to t of n times log n to the second power. This is the time complexity of this problem. Divide and conquer algorithm, dynamic programming. So, what is dynamic programming? Dynamic programming is actually the extension of the divide and conquer algorithm. When the divided problems appear over and over again, or when the problem has a fixed pattern, we will use memory methods such as arrays or serials to store our sub-solution. What are the advantages of this? That is, we can avoid finding the solutions repeatedly. The process of dynamic programming is to read data, calculate data, and store data repeatedly. We can get a wide range of solutions from a small range of data, after analysis, judgment, and combination. The two most important elements of dynamic programming algorithm are state design and equation of transfer. For example, the equation of transfer for the Fibonacci sequence is fi equals fi minus 1 plus fi minus 2. Dynamic programming often uses two-dimensional arrays or even multi-dimensional arrays, so how to use multi-layer loops to control the index value of the array requires more attention during program practice. Application of divide and conquer algorithm, the longest common subsequence. Next, we will use the longest common subsequence to illustrate. The longest common subsequence is defined as when we have two sequences of numbers or strings, we want to find out what the longest common set between them is. For example, we now have two sequences of numbers, S1 and S2, and their sequences of numbers includes 1, 3, 5, 7, 9, 11, 13, and the second sequence of numbers includes 1, 1, 2, 3, 5, 8, 13, and the common set between them is 1, 3, 5, 13. At this time, our LCS, or the longest common subsequence for S1 and S2, is 1, 3, 5, 13. The same method can also be used for string comparison. For example, the string S1 is student and S2 is tied. So we can see that the letters that appear in both of them are T, D, and E. Now we know LCS S1, S2 is TDE. There are many applications like this in real life. For example, the comparison of gene sequences, etc. So, how do we solve the problem? If we split the two sequences S1 and S2 into the previous sequence plus the last element, for example, S1 equals sub 1 plus E1, S2 equals sub 2 plus E2, then we can assume that S1 is 1, 3, 5, 7, sub 1 is 1, 3, 5, and E1 will be 7. For the part of S2, can you think about how S2 will be disassembled? After being disassembled, there will be 4 situations for LCS S1, S2. The first one is LCS S1 sub 2, which includes E1 but not E2. The second one is LCS sub 1 S2. This way, it does not include E1 but includes E2. The third one is LCS sub 1 sub 2, which does not include E1 nor E2. The last situation is LCS S1 S2 plus E1. This is when E1 and E2 are the same, and we will get the longest common subsequence. What we did just now is the state design for the problem. Next, we will design the equation of transfer. When E1 is not equal to E2, our longest common subsequence will be equal to the maximum value of LCS sub 1 S2, LCS S1 sub 2. When E1 is equal to E2, our longest common subsequence will be equal to LCS sub 1 sub 2 plus E1. If we use the two-dimensional array LCS I, J, to represent the length of the LCS of the first I elements of S1 and the first J elements of S2, then LCS I, J is to find the maximum value from three directions. First, we assume the values of S1 and S2 and set the length to be a two-dimensional array of 8 by 6. Next, we are going to initialize the length of each element to 0. When S1 or S2 is an empty set, then LCS is an empty set. Next, we are going to fill the form according to the recursive formula. The first condition is when E1 equals E2. LCS S1 S2 will be equal to LCS sub 1 sub 2 plus E1. When E1 is not equal to E2, our longest common subsequence will be equal to the maximum value of LCS sub 1 S2 and LCS S1 sub 2. The concept of the longest common subsequence is actually related to the comparison of gene sequence codes. When our two strings are AGA-CTG-TC and TAG-TCA-CG respectively, we can try to compare them manually first to see whether we can find the LCS. The rule is some of the characters in the two English letter strings can be omitted, but the alphabetical order cannot be changed. Let's connect them. AGCC. We found that the first possible longest common subsequence is AGCC. Are there any other possibilities? Let's change the middle ones. AGTG. Next, let's try looking from the middle. TGTC. Try again. AGACG. This combination has 5 English letters. It's longer than the 4-letter combinations we previously found. In fact, AGACG is the longest common subsequence of this question, but trying it one by one is definitely not the way to go. Let's visualize the string comparison. We can put the two strings AGACTGTC and TAGTCACG into the form and set them as the top row and the left column respectively. How do we fill out the form? When the top row corresponding to the form matches the left column, add 1 to the value of the grid. If there is no match, select the larger value on the left or top to fill it in. So let's fill in both rows with 0 first because they have nothing to the left or above. Then start filling in the A and T grids. You can choose to fill in horizontally or vertically. Then use an arrow to mark where the value came from to facilitate the use in subsequent steps. If the value on the left is the same as the value above, we will uniformly mark the upward arrow here. The first match we have here is T. The upper left grid is 0. So the value is 0 plus 1, which is equal to 1. Mark the arrow towards the top left direction. The next grid has no match, so the left is 1 and the top is 0. So write down 1 at this time. Next is TT. Match successfully, but remember to plus 1 to the top left value. So do not write 1 plus 1. This is still 0 plus 1, which equals 1. Okay, let's go to the next row. AA matched successfully. The upper left corner is 0. 0 plus 1 is 1. AG match failed. The maximum value on the upper left side is 1. Fill in this grid with 1. AA matched successfully. The upper left corner is 0. 0 plus 1 is 1. AC1, AT1, AG1, AT1, AC1. For the rest, you can take out a piece of paper, pause the video, and try to write it yourself, and then check the answer. Are you done? Then let's continue. When you complete this form, the value 5 actually means that the length of the longest common subsequence is 5. And through this form, we can also find out what the LCS is. Please start with this 5 and follow the arrow upwards. You will find that the ones going up and left diagonally are all matched letters. So we can list our LCS as A, GACG. Application of divide and conquer algorithm, 0-1 backpack problem, assuming there are n items and one backpack, and weight W and the value P of each item are known, and the maximum load-bearing max of the backpack is known. Under the weight of max, what is the maximum value that can be loaded if the item cannot be divided and repeated? First, we assume that there is a backpack with a maximum load-bearing capacity of 15. In addition, we have 5 items. The weights are 12, 1, 4, 1, 2, and the values are 4, 2, 10, 1, 2, respectively. One way is to take the first, second, and fifth items. The added weight is just equal to the maximum load-bearing capacity of 15, and the value is 8. But this result is not the best. Because if we only take the third item with a weight of 4 and a value of 10, it is already better than the result above. If we use the exhaustive algorithm with the two states of taken or not taken for the n number of items, there will be n to the power of 2 kinds of results. When n is very large, it will take a lot of time. When the load-bearing capacity of the backpack max is smaller or there are fewer items, it may be easier to solve the problem. So we will create a two-dimensional array of dp and max to dynamically program our problem. dpij means that only the first I items are considered, and what is the maximum value that can be obtained by putting them into a backpack with a maximum capacity of j. So we can get the equation of transfer of this problem as dpij, that is, the maximum value of dp I minus 1, j, and dp I minus 1, j minus w I plus pi. That is, the value of the I item is not taken, and the value of the I item deducting the weight of wi. And finally, add the value of pi, which one is greater. Actually, we do not need to use a two-dimensional array. This equation of transfer can be modified to dpj equals dpj minus wi plus the maximum value of pi. Next, we are going to discuss the program code of the backpack problem. First, we need to determine which parameters and arrays we will use. Then read the weight of the backpack and the number of items, and what the weight and volume of each item are. Next, we are going to discuss 2 situations. When the maximum load of the backpack is less than the weight of the item, when the weight of the backpack can still bear the weight of the items, we will compare the original value of dpj and the value of pi obtained by taking wi. Finally, output the result. If the input is according to the conditions of the backpack and the items just now, you will get the answer of 15 as the highest value that can be put in the backpack, which is the result of not taking the item with a weight of 12. Divide and conquer algorithm key point review. First of all, what are the 3 steps of the divide and conquer algorithm? The first step is to decompose, then to solve, and finally to compose. And what were the 2 methods that were used in this chapter to achieve divide and conquer? The first was recursive. The second was dynamic programming. And what problems arose when we used the recursive method to solve problems? The first is, what parameters do we need to pass? What is the termination condition of the recursive subroutine? Next, what data do we need to calculate? And what information do we need to return? Is it necessary to calculate or compose? When we use dynamic programming to solve problems, we have 2 constituent elements, state design and equation of transfer respectively. Let us take a look at the longest common subsequence in this unit of divide and conquer. This question hopes that we use a program to find the length of the longest common subsequence among the 2 sequences. Here, we just need to find the length. Let us first look at the definition of the longest common subset. For example, if we have 2 sequences of numbers to compare, you can find that these 2 top and bottom sequences of numbers will have at most 1, 3, 5, 13 coincided. Then we will say that their longest common subsequence length is 4. One of the data in it will be 1, 3, 5, 13. Sometimes there may be several longest common subsequences. But today, we just need to find the length first. If we compare the strings, like these two words, it can be found that the most in those are T, D, E. These three letters are exactly the same. The order cannot be changed. The order cannot be changed, so we have T, D, E, which is their longest common subsequence, so the length will be 3. What we want to find is the length of their longest common subsequence. Let's try to write this part of the programming code. Similarly, let's take care of the formatting first. Then we use function to do it this time. Use void, and we'll just name it to find the longest common subsequence. So our main programming code is extremely simple. We just need to call this function. Then, because it is a bit more troublesome for us to import the parameters, so we can just set variables directly here in global. This way, I don't have to keep importing parameters. We'll input the data we want to find directly, and you can set up these data at will, or set the same things that I have set up. 2, 5, 7, 9, 3, 1, 2. This is the first S1. For the S2 part, we set up 3, 5, 3, 2, 8. These are the two sequence of numbers we set up that we want to compare. Next, we will need a part to help us process them later. This number of grids will be one more grid than our sequence of numbers. Is that okay? S1 is 7, so we use 8 grids. S2 is 5, so we use 6 grids. This is a two-dimensional array. Let's save it. Use the idea of dynamic programming to do this problem. Let's write this function. In the function, first of all, we will set up the form boundary of the dynamic programming first. For the boundary, we'll set them all as 0. Here you can use I++ or ++I. Both can be used. Both of them are the same in this situation, I++ and ++I. They're only slightly different when they are saved. But in this situation, they're the same. There's a saying that ++I will be faster. So don't be scared when you see it. It is the same as ++I, I++. The other side is also the same. We fill in both the leftmost and uppermost grids with 0. The other grids depend on what kind of computation it does. What is the length? When are we doing calculations? We will start filling out the form from the position of 1. So I is equal to 1. I is less than or equal to 7 ++I. Because this is a two-dimensional form, we need 2 layers of loops in order to fill out the form. J is less than or equal to 5 plus plus j. After the form is done, let's start filling in this form. How the form is filled in is what we are going to compare. Is our data the same or not? Like this one on the side, 1 and 1 are matched, so the length of our longest common subsequence will increase by 1. Of course, 1 is not added randomly. It depends because the next one is also 1. 1 and 1 are matched, but I will not make the longest common subsequence 2. So when we are comparing, if there's a match, it is necessary to add 1, but 1 is not added randomly. Here, since our I and j started from 1, but the numbers of S1 and S2 both started from 0, so we must remember to use I minus 1 and j minus 1 to make judgments. For the judging method, if you find that they are equal, make sure to add 1 to this grid of ours. But the situation of adding 1 depends on the grid in the upper left corner. Add 1 to the data in the grid where I and j are both subtracted by 1. This way, we won't add it to the wrong grid. You can find that these ones are the same and these ones are also the same. So the grid in the upper left corner will be used for processing so that 2 will not be added accidentally to something that is clearly 1. If there is no match, we will choose the larger number on the top or left of it to fill out the form. Fill in the form with the larger number on the left or above. This way, the filled out form will be the programming code of our longest common subsequence. I am not going to use parentheses here so we can see more things. There is only one line anyway. Then in the end, we just output the length of the longest common subsequence. We will save the length in the last grid of this two-dimensional array. Our two-dimensional array is a total of 8 grids by 6 grids. Because we are from 0 to n minus 1, so our last grid is number 7 and number 5. That grid will be in the position of the last grid. This is how we write the programming code of the longest common subsequence. Let's execute it. It will get the result of 3 for the longest common subsequence. We can look at these two data. Here the comparison we got was 5, and this is 3, 2, which is the longest common subsequence. You can also change some of the numbers to give it a try to see whether the program code you wrote is correct. For example, I changed the first 2 to 1 to give it a try. This way, there should be an additional 1, and it will become 4. This is how the longest common subsequence is written. Everyone can pause a moment and think about how to do this. Okay, please complete this question. Let's take a look at the 0-1 backpack problem in this unit of divide and conquer. Suppose there are n items and a backpack. The weight W and value P of each item, and the maximum load-bearing capacity of the backpack max are known. Under the premise of max weight, and items cannot be divided or processed repeatedly, what is the maximum value that can be put in? This means that your items cannot be cut. So it just keeps that weight. If its weight is 10, the weight you put in each time is 10. You cannot cut it in half and turn it to 5. Cannot be repeated means that each item can only be taken once. They cannot be taken separately, so there is only one of each item. That's what it means by not repeated. Similarly, let us work on the format first, and then think about how to write this program. This question is not the same as the backpack question that we did for greedy. In the previous backpack question, they could be divided. That has a greedy strategy to find the highest CP value, but we cannot just look at the CP value for the 0-1 backpack problem. If you only look at the CP value, it may be wrong. For example, maybe my backpack has a maximum weight of 15, and the max is 15. Then I have something with a weight of 10, and a weight of 8, and a weight of 7. Something like that. Assuming the weight is 8 and its value is 8, the weight is 7 and the value is 7, and the weight is 10 and the value is 12. If we only look at the CP value, it seems that the item with a weight of 10 has the highest CP value because its CP value is 1.2. But if you look at the item with a weight of 10, you only have the space of 5 remaining in your backpack, and you cannot place anything else, so the total value will be only 12. But if you put the two items with weights 7 and 8 instead into the backpack, you can get a total value of 15. So you cannot just look at the CP value in the 0-1 backpack problem. This is the main difference from the previous question of greed. Now, let's think about how to write the programming code for this backpack problem. First of all, we will let the user perform input. What we want to input includes the largest load-bearing capacity and how many items there are. Then input the weight of all items and the respective values, etc. So, we set a few variables for processing: maximum weight and number of items. And what is the weight of each item? And their respective values. We will also need a dynamic programming DP form so that we can perform input. Input the maximum load-bearing capacity first, then input the number of items. The next step is to input individually the weight and value of every item. So here, we can use the for loop for processing. Input repeatedly. Then we will input the weight and value of each individual item. We will use the for loop for the input here. More particularly, we are going to start from I equals 1, then I is less than or equal to n, then I plus plus. This is to be used with the DP table later. Such input is less confusing. Then save these things in the W and P arrays. Next, we're going to fill in the form. For the form filling, we also start from I equals 1. I is less than or equal to n, I plus plus. Then, another loop J. J will be equal to our biggest backpack load bearing at the beginning. We want to see what kind of different results there will be for different backpack weights. If J is less than the weight of the item, this J loop here will appear, meaning that no other items would fit. If it can hold more, we will fill in the form. For this grid of J, we can fill the grid with D, P, J, and DP to compare values after placing items inside. Take a look. If we put the I item in the backpack, J, our J backpack will have less space after putting it in, but the value will increase. Value added. Although I have less space, the value has increased. So the value added and the originally larger J backpack, which one is more valuable? We choose the higher one to fill in the form. This way I can know how much value of items I can place in my J backpack. Then finally, for the last grid, that is, output of the grid of backpack load bearing. And this is how the programming code of our 01 backpack question will be written. Let's use a small example earlier. The load bearing is 15, and then there are 3 items. The first item is 10, and the value is 12. The second item is 8, 8. The third item is 7, 7. So we will output 15. This way, it will know that I don't want this one with the highest CP value of 10. Instead, I want these 2 items with the highest total value. That's it. Everyone can take a look again. Think about why the programming code was written this way. Or you can review the tutorial video. Please finish this problem.